Right, what we need to do, we need to split our vectors into initial, final, horizontal and vertical components. Now there is a slight typo there. These two equations, useful equations for the two, include horizontal x. Now in the x, what I would ask you to write here is that ax equals 0, meaning that there is no acceleration in the horizontal. And then the equation that we use is quite simple. It's s equals ut. That's it. S equals uxt. Now if we have the angle to the horizontal, then that's simply going to be u cos theta times t. Okay? What do you want?
One of the, is this it?
No, I don't have any left. Are there any spare booklets around the tables? Okay, thank you. I might not have printed enough. There you are. Next. Over on this side, we'll say that ay is acceleration due to gravity, which on Earth we will use 9.8 negative. Now be careful here. There was a question in a couple of years, an exam, WACE exam from a few years ago. The projectile motion equation was on the moon, so you had to use the moon's gravity, which is actually in your data sheet as 1.60. Lots of students got caught out that they did the whole question using 9.8. Now, the equations we can now use are as follows, and here's where I'm going to try and remember my prefixes, that v equals u plus at, and also a equals v take u over t. So you notice I'm using the subscripts. Next, s equals ut plus a half at squared, and now v squared equals u squared plus 2as. So now it's becoming important that we know that these equations are only reserved for the y component, because it's only the y component that there is an unbalanced force. This is ignoring the effects of air resistance. Now in the learning outcomes that SCARS are put out, you only need to be able to explain qualitatively the effects of air resistance. To quantitatively calculate the effects, it becomes much, much trickier. It becomes a second order differential where the air resistance affects the velocity, which then affects the air resistance. And so the mathematics is too complicated. So we use the simple model. You will often see questions that state ignoring the effects of air resistance. And as soon as you see that, it's a simple quadratic model. Okay? Now, I did ask you before to be able to split your vector into horizontal and vertical components. So let's just remind ourselves of the equations. We might need to include that theta is there, and then ux is u cos theta. Okay. Now, I would like you to now sketch not a position time graph, but a position graph. So we're going to have sy on the vertical and sx on the horizontal. What I'm next going to do, and just wait because I'll probably stuff it up, but I'd want you to plot the position of the projectile at every 1 second interval. And I'm trying my darndest to sketch out a quadratic. Okay? Not the greatest. I reckon this little dude could go down a little bit. Okay? Try your best. So, I next am going to sketch the x component. And for this model, it's going to remain the same magnitude. So what I need you to appreciate is that every 1 second interval, the vertical component remains constant. So try your darndest to sketch your horizontal component as a constant length. Okay? And then I'll use the same color now. What we can now appreciate is that the y component is going to change by negative 9.8 every second. So I'm going to start off with 29.4, and you might notice a reason why I've done that. And then the next second, I'm going to reduce that by the rate of 9.8, so now we're at 19.6. And then in the next second, I'm going to reduce it further, and now it's 9.8. And then at the third second, we are at the turning point. So there would be 0 component. You might want to just make a note here, uy equals 0. Okay? At that turning point, the velocity is exactly the horizontal component. So for that brief instant in time at t equals 3.00 seconds, there is no vertical component. It actually changes direction, because remember, gravity is constant. The rate of change is constant. We are then going to continue such that 4 lots of 9.8 will give negative 9.8. Then 5 lots would give negative 19.6. And then finally negative 29.4. Okay? So we've got these brief snapshots in time every 1 second, and we might want to say that that's u. This might be v after 1 second. This might be v after 2 seconds. That's v after 3 seconds, etc., etc. Okay? So, no, velocity. So, at any time, we can figure out the speed of the projectile. We should know that the horizontal remains constant, and the vertical can be expressed as v equals u plus at. Okay? So let's just quickly throw in an equation here. That's just v of t, or in fact it's vy, equals u plus at. So if you know the initial condition and you're given the time afterwards, you can figure out what it's doing vertically, and then you can combine it. Now, there's no need to, we could join these in some sort of weird parabola to show that it's path, but hopefully you guys know that it's tracking out a parabola. There's one other, what else do we write up here? At the turning point. So, I already mentioned this, but let's just put it down. At the turning point, Vy equals 0. The time is negative b on 2. We'll mention this on another page, but in maths talk, it's negative b on 2a, which in physics talk is negative uy on g, but more about that later. There's one other important equation. Let's consider the horizontal displacement, which is known as the range. Well, that's just uxt, as was mentioned on the table. That's u cos theta times time. This is known as the range. Okay? Easy, easy. Can we go over the page? Yes or no? Yes, no, maybe. Yes? Can we move on? All right. So obviously you see there I made 6 very nice easy intervals of time, such the third was at the middle and it's perfectly symmetric. You should notice that on the downwards path it's the same magnitude but in the opposite direction. Okay? Can I move over now? Thanks. All right. An object fired horizontally will fall the same vertical distance. So this is a bit tricky to draw, but if you draw an object every second, obviously the distance that it's falling gets larger and larger. 1, 2, 3, 4. Okay? So, t equals 0, t equals 1, t equals 2, t equals 3, t equals 4. This again is still a SY. Now, do we want time? No, let's go SX in meters. So So often there's some lovely questions that pop up that sort of say an object falls. I'm not really happy with this first one. Let's move him up a little bit. And him, I'm still not happy. Let's move him up a bit. It's a bit tricky to draw the square function. So now I'm going to try and draw my objects the same distance. This is not really working, but let's just quickly draw it in. So let's use the information given below. Let's suppose that an object is fired horizontally. Well, that means that uy equals 0. If you fire something horizontally, it has no initial vertical component. This is the easiest one to start off with. Later, we will fire something above. It's called an oblique projectile. Or below the horizontal, it's oblique. But for now, you will notice when we work out the maths, when uy is 0, often the equations are simplified. They're a lot nicer. You don't have to use the nasty quadratic. But again, if that's our horizontal, just to get it ingrained, could you please sketch, as we did before, that we know that the horizontal component remains unchanged. We've got here not sy, that's s, displacement. No, it is sy, I wrote sy. Negative 100, and that was ux. Okay? And so the question is t equals question mark. Well, again, t1, t2, t3 and t4. We know that the y vector is increasing by 9.8 every second. It gets longer by that amount. So if we go to this question, we've got s equals negative 100, a equals negative 9.8, uy equals 0. In fact, remember, I keep forgetting to put in my subscripts. T equals question mark. So this is a nice equation. As I said before, Jesus, that's a bit bold. Let me just drop that down a bit. We know that that term goes to 0. And so if we rearrange for t, we're going to times both sides by 2. Divide by a and take the square root. All right, I hope we're happy with me doing those steps all at once. Eric and Trig, Pan and what are we laughing at? What are we doing? What are we? So you're just scoffing about it? Scoff quietly, please. Thank you. We get a time of, help me out here because I don't think I've solved it, negative 200 over negative 9.8, square root of 20 point something, 4 point what? 4.52 seconds. Thank you very much. That's the time taken for it to hit the ground. I don't know why my direction of S decided to change to red, but let's just go with it. So we know that's how long it took to hit the ground. Okay? That could then, we could now go back, because we have the space. What the hell's going on here? That's better. We could figure out Sx. Well, that's just going to be ux times t. So that's 20 times 4.52, which is, 90.4 meters. All right? So once we've solved for the total time, we can multiply it by the horizontal velocity. That gives us the horizontal displacement from the start. Now, I'll need you to sort of go, why the hell did Mr. Murray ask for 5 seconds when it hit the ground before? So, could we pick 3? You could pick any arbitrary time value between t0 and t final. We could figure out what it's doing and where it is. So what it's doing, we could figure out its velocity at t3, and we could figure out its displacement at t3. Okay, or where it is compared to where it started. So, could we do that now? Our velocity. I'm going to sketch the approximate velocity. There it is there. We know that Vx equals 20. And so what we now need to find is Vy. So it's not too tricky. It involves Pythagoras and trig again. Vy equals uy plus ayt. Again, so setting that to 0, minus 9.8 by 3. It has a vertical component of negative 29.4, I think.
Yeah.
Okay. And so we can solve for velocity and would somebody mind solving that for me? It'll be more than root 2 times greater, so it's more 35.6. Same deal, let's get a theta. Oh, hang on, which angle do we want? Do we want the angle with respect to the horizontal? I think we do. I think we want theta. So let's say theta equals the arctan. From my diagram, it's Vy on Vx. So that's 29.4 on 20, which will give some angle greater than 45. Help me out. It's been a long day. My sinuses are getting congested.
55 degrees, 56 degrees below the horizontal.
55.8. All right, so yep, again, final answer, 35.6 meters per second, right at 55.8 degrees. Okay, let's bring out this bad boy.
Draw straight line shapes.
Oof. I know. Oof. Okay. Apparently the term oof originated from Roblox. I'm too old to know Roblox. But anyway.
No, I think what a generation we live in.
How do I get rid of my ruler? There we go. And then the range after, let's go the same 3 seconds. Oh, sorry, the horizontal range. So that just basically means on our diagram, 1, 2, it's basically, could you please tell me, dunk, SX. Okay? Yeah, pretty damn easy, 60 meters. But since we got the space, let's go one step further and determine displacement. So same deal, from point A to point B, we've just figured out the horizontal displacement is 60 meters. The question is, how far vertically has it fallen? Well, that's just going to be S equals UT plus a half AT squared. So we have an equation for an object that's falling under an accelerated rate. A half of gravity times 3 squared, 4.5 lots of negative 9.8 is what? 45 less 0.2, 45 less 44.1.
Yep.
Thank you, me. All right. So if you were ever asked to find the displacement of the ball, remember straight line distance from start to finish, and you could figure out the displacement and the angle. That's not very a useful value for us. It's basically on the diagram, figure out that arrow, that vector S, which is not normally that useful. There is another, this is not in the syllabus, but there's something called the path distance, which there is a nifty way, if you know the equation of this curve in both x and y, then you can do this integral it's something like the integral of the Pythagorean. So you take the s of x squared plus the s of y and the square root of it, and then you integrate. There is a method, but it's way beyond the syllabus. I've forgotten it. Again, you could investigate it. You could Google search path length of a curve, and you know, some of the kids doing spec methods might be able to play around with it, but I'm not going to because I'm not smart enough. All right. The effects of air resistance. This is what you are expected to explain qualitatively. Zach Jacobson. Yeah, just nod and thumbs up. Thank you. Yep, cool. Don't draw that. Try and draw a perfect quadratic as best you can. And I will color code that the black line is no air resistance. Okay. Obviously, this is a SY in meters and SX in meters. Please draw a position curve. And we're trying to draw a perfectly symmetric parabola. I'm not happy with that parabola. I'm going to try one more. Do we have shapes? No, we use stupid shapes. Is that better? No, that looks better. Into shape.
Into shape up the top, and you just draw it, and it'll like guess what you're drawing.
Nah, didn't. All right, okay. Could you just highlight the turning point for me? Now, gentlemen, could we highlight U, and we'll call it. Ooh, it's doing that funny thing.
So it's taking over a straight line and actually making the line very.
Thank you. That would have taken me minutes to figure out. All right. Could you please label the initial velocity? Toby, shush. Go outside and talk. Could you label theta initial, which would obviously be the initial angle of the projectile? Now, here's what I'd like you to do. With just a sort of a dashed line, I want you to start to peel away and make a turning point before the red line, below the red line. And then as you peel down, I want you to sort of just drop off really quickly, such that it is not symmetric. Okay? So that's kind of the shape comparing the trajectory of your projectile without air resistance and with air resistance. Okay? And then, obviously, I want you to call that theta final. So, obviously, there's a number of differences. I'm going to draw about 5 dot points off to the right, and I'm just going to make the statement. But you then need to be able to state and explain that phenomena. So the first one is that the maximum height is reduced. Okay, so write that down. Obviously, the object does not get as high when you consider air resistance. There is a reason for that, and the reason is that air resistance is going to oppose the motion in both x and y. So now what I want you to think is, without air resistance, the only force acting is a downwards vector which we call mg, weight. And that causes a constant acceleration which causes a lovely parabola that describes its path. With air resistance, on its way up, not only is there a downwards weight vector called mg, but there is now also an extra vector acting downwards called air resistance. So with air resistance, the net force, or the sum of all forces, is now greater than weight. So I'm just going to summarize it very briefly, that the sum of all forces is greater than mg. Therefore, your acceleration is greater than g. And if you throw in a number that's greater than negative 9.8 into your s equals ut plus a half at squared, you're going to get a smaller value because the rate of deceleration is greater in magnitude. Okay, so you should be able to state the 5 dot points and obviously elaborate on this. This is summarized, so you'd want to be able to throw it out in a sentence. Next, the range is reduced. For pretty much the same reason that if our velocity has an x component, then so too will the component of air resistance. It has a backwards component. So now you can say that the sum of all forces in the x is no longer equal to 0. That there is there's a backwards component, and so there's a backwards acceleration. So now, if we find the total time of the flight, your range equation can no longer be expressed as uxt. It's uxt plus a half axt squared, which is in the opposing direction. So you're going to be going that way while slowing down. And if you're slowing down, your range will be reduced.
Wouldn't axt squared be changing?
Ax
squared. Wouldn't ax be changing?
Well, that's the problem. That's why we're only asking to explain qualitatively. To try and calculate it, then it's a second order differential. That the velocity in the x influences the resistance, which influences the acceleration, which influences the velocity. Right? So you get this kind of, the change in a variable affects the overall rate. So that's why we can't do it at a year 11 level. You could go to university and model this in first and second year mathematics and science. Okay? So, with that in mind, could you please sketch on our trajectory a ux and a vx? And I need you to draw vx reduced, as we just said. If there's a backwards horizontal force, then that's going to reduce the size of my horizontal vector. So you can see I've drawn, hopefully, my initial horizontal greater than my final. Okay? That will hopefully explain the next couple of points, that we are asymmetric about the turning point. And then you can use these dot points to basically guide how you would sketch the air resistance trajectory. If there was a 4-mark question, sketch the trajectory of a projectile with no air resistance and then sketch it with. Well, you'd use these dot points. So you'd have the maximum height reduced, the range is reduced, it's not symmetric, and the last one is the angle, the final angle is steeper. Hits the ground at steeper angle. So in my diagram, it would be theta final greater than theta initial. Okay? Now, you can't really see this last dot point on the diagram, but your time up is going to be less than your time down. So it actually spends, without air resistance, everything's equal and symmetric, time up equals time down. Here, your uptime is less than your downtime. Now have a think. It goes back to our first statement about the net force and which direction it's acting in. So on the way up, you've got an acceleration or a rate of change that's greater. It's going to cause you to be stationary sooner. Yeah? Sooner. You'll stop quicker. Time up is less. Did I write it correctly? Yes, less.
Acceleration
greater. So it'll slow you.
magnitude.
No, so to get to v equals 0, if a is bigger in magnitude, t will be less. If you're accelerating at a greater rate, it'll take less time to get to v0.
It's acting downwards though.
when it's on its way down, the opposite occurs. Air resistance acts upwards. Your acceleration is less than gravity, and so the rate of re-acceleration is less, and it would take a longer time to accelerate back down the same distance, same displacement. So I recall maybe my first or second year, Dr. Zander threw a lovely question in a year 12 test or exam. You throw an object up into the air and you catch it at the same height. Does it spend more time on the way up, more time on the way down, or the same time up or down?
With air resistance.
With air resistance, thank you, yes. So with air resistance, it spends more time on the way down. On the way down, air resistance is acting like a parachute. Have a think, if you deploy your parachute, you've got this upwards air resistance. And so when you combine the weight force and the air resistance, the net force is reduced. Okay. Now again, as we get closer to WACE exams and we come back to revise this stuff, in 14 weeks' time, I'll find you some questions that have appeared in the past 5 or 6 years of WACE exams and go, look, this question appeared. And this is the one that tricked a lot of students because they didn't see this. Now again, you can't spend too much time preparing for the WACE exams by looking at what they've already assessed in previous WACE exams. Because they're never going to they're not going to say, oh, that was a really good question, let's put it in next year. But what you can do, and this is what Roy Skinner does in his Krillman book, is he goes, in the past 6 years, they haven't asked a question about this. Or there hasn't been this kind of projectile motion. So you can almost kind of have a guess or a prediction as to, well, that hasn't been asked for a while. Maybe this kind of question might appear. Okay, so when they make the exam panel, they start in January and they've got to get the exam prepared by June or July. They need to, obviously they'll make the exam, they need to make sure that there's no similar questions that have occurred in the past few years. And so again, once you start going, well, I can't ask that question, I can't ask that question, there isn't too many ways to ask a projectile motion question. And so that's, what I try and do is go, this is what my guess, my pick of the year is that there's going to be a question like this, and hope. So again, I try not to spend too much time on this question was in last year's exam because it's not going to be in the exam that you're going to do at the end of the year. I'd like to just finally show you a lovely question, a lovely equation that manifests when we ignore air resistance. Could you please sketch your lovely oh, wow. Whoa. Did I just eat to shape there?
No.
Whoa. Sketch your lovely... This one's going on the YouTube, isn't it? Can you sketch... Oh, wait, not a position time, please. Position time. Position time. You can throw in your U and theta if you want. But what I'd like you to do is to slice this about the turning point. And again, I'm going to just quickly, just for reference, for those of you that may have forgotten, you've got y in form of x is ax squared plus bx plus c. Now I would like you to write sy as a function of time is a half of gravity t squared plus u sine theta t plus s initial. Okay? So again, recall that that's always going to be minus 4.9 and that's always going to be uy. Okay? Now, our turning point... calm down. Our turning point equation in maths is negative b on 2a. If we were to look at the physics, it's going, well, negative b is negative u sine theta over 2 lots of a half of gravity is just gravity. So now I've got t up. I know from start to turning point, t up is negative u sine theta over gravity. Quick little side mission. If you wanted to find the turning point, you would set Vy equal to 0. Uy is u sine theta, and AY is AY. And so you could go, well, T equals V take U over A. Sub in V equals 0, you get 0 minus U sine theta over AY. Well, that's, come back negative. That's what we found looking at the turning point equation. It's exactly the same if you use your equation of motion and set Vy equal to 0. I forgot all my Y's. There are little Y's there, you see? Cool. Let's keep going. If we ignore resistance, everything is symmetric. And then I know that T down is also negative U sine theta over G. Just back to the turning point. The turning point depends on three things now. How fast you throw it, at what angle you throw it, and the gravitational acceleration that you're in. Obviously, if theta is straight vertical, then sine of 90 is 1. And the equation just becomes negative U over 9.8. As we start to reduce the angle that it's projected, you're going to reduce the time because you're reducing the vertical component. Okay, so next, if I was to make the following statement, let's just throw in the range equation here because I like to sort of give it its space where it belongs. Let's do it in 2 steps just so I'm not skipping any. That's Ux times time total. I'm just going to use time total. That's U cos theta times time total. Okay, so next statement. I'm going to say that time up plus time down will give us the total time. And not only that, time up equals time down. In that case, time total is 2 lots of negative U sine theta on G. So I could make an expression, well that's negative 2U sine theta over G. So the total time is the same as the turning point. It's dependent on 3 things. How fast you throw it, the angle that you throw it to the horizontal, and the gravitational acceleration that you're in. I'm going to call this equation 1 because we have an equation for T which we can sub in to something else. Yes, Marcus?
No, never mind.
Okay. Yes? Can you what? Oh, but you're missing the best part.
Is it Sx equals U squared sine 2 theta on G?
Well, yeah, but how did you know that?
Because it did.
You were looking at my OneNote earlier today, weren't you? Get out of
No,
here. You can watch the last 5 minutes of the YouTube video, which will go up in a few. All right. So now let's bring our range equation down here. Sx equals U cos theta times time total. Now, that's my equation 2. And I'm going to sub my time equation into my range equation. And I get the following. U cos theta times negative 2U sine theta over G. Let's tidy it up. Negative 2U squared sine theta cos theta over G. Here's where we take a little side mission. And this is why it's not going to be expected that you derive this in a test or an exam. I just thought I would show you because it's fun. There is a trig ID that, I've forgotten it, 2 sine theta cos theta equals sine 2 theta. And so if I was to highlight, I am highlighting it. Look, it's, God dang it. That is right there, 2 sine theta cos theta. So I'm going to replace the highlighted bit. That's negative U squared sine 2 theta over G. And this is our range equation for level ground. It only works for level ground because it's only on level ground that these statements are correct. If it's not level ground, then T up does not equal T down, and you can't simplify it to 2U sine theta over G. Okay? Now, again, the range of a projectile still dependent on the same 2 damn bloody things. The speed that it's thrown at, the angle to the horizontal, and the gravitational acceleration that it's in. Okay? Now, if you've got some room, before the maximum height equation, that's for tomorrow, we're going to quickly sketch, very simply, the optimum angle. What angle would give the greatest range? Basically sine 90, right? We need sine 90 because sine 90 is 1. That's the biggest sine that you can get. Well, if 2 theta equals 90, then theta must equal 45. And so that would be our 45. Okay? Now, we're at the top of the unit circle. I want you to imagine a semicircle, we're at the top. And we could split off both ways, either side of 90. So what I'll show you is if I fired something at 30 degrees, we would get that. Because sine of 2 lots of 30 would give sine 60, so the range would be reduced by sine 60 of the possible maximum. But there's also you could go a low angle and it would get to that horizontal distance, or you could go a high angle and you would get to the same. And so if you've got sine 60 on one side, which is 30 back from 90, you could go sine of 120, which is theta equals 60. So there's only 45 will give you one range, and it's the greatest. As you bring it back, you get two sort of, are they called complements? Does 30 and 60 complement each other such that sine of 2 of them gives the same? And so you could then start peeling your way back. If I went 10 and 80, does sine of 20 equal sine of 160? I think it does. You could keep peeling back and go, I'm bad at maths. 50 is 40 back. 50 and 130. So maybe sine of 100 and sine of 130. I don't know, I'm running out of ideas. Now, hold on. There's going to be 2 extension type questions that I'm going to show you. There's going to be 2 extension type questions. Just listening, please, gentlemen. I know you're very excited. You've seen a lot of very exciting equations. If I gave you the range and the speed, there are 2 angles. But unfortunately, to solve that nasty question requires another nasty trig identity, that tan theta equals 1 on cos squared theta, some weird one. Did I say it right? Yeah? It's not in the syllabus. So again, I will show you the derivation, but I would put the disclaimer, not in syllabus. All right? So don't worry, you don't have to show that derivation because it's not a prerequisite to know method and spec. Students can get by doing maths apps. And in maths apps, there is not so much of an emphasis on trig identities. Okay? So because of that, we cannot ask you a nasty question in physics that requires stuff that apps kids couldn't get. Okay? So normally there's around about, I think the ratio might be about 80%, 20% methods to apps. So I apologise if I'm spending a bit of time on stuff that 20% of the students might not be familiar with. But we will leave it there, gentlemen, and I will see... Oh, hang on, can I talk to you for a bit more? On Wednesday, I am going to be away doing Ad Astra. So have a look at my timetable. I don't see you tomorrow, but I see the other class. So what I'm going to do is screen capture that lesson, and you will be on Wednesday. I'm going to give you your task in class will be to bring some headphones and watch the lesson, the Tuesday's lesson, which for you is Wednesday's lesson. Okay? So please, everyone bring headphones. I will email you a reminder. I won't be here on Wednesday. You'll get a relief, teacher, but you're just going to sit there with your headphones in and copy down the booklets as normal. Okay? Thank you, gentlemen. See you later.